Hi there students, as I promised I've made screencasts of the questions in the worksheet that I gave you guys last week, or not last week, the week before. And so let us start with question 1. It's a good idea, as I've mentioned in class, to always write down, as we read questions, to write down the things that we identify. So let's start with reading this question. Mary Watkins has kept a record of her commute time to work since she started working at CPUT. The accepted commute time from Mary's house to CPUT is 40 minutes, so that's an average. Also, something that should stand out for us is the use of the word accepted. This tells us that this is a population parameter. It is known information and known data. With a standard deviation of 10 minutes. Because this is population data, that average is mu. So mu is 40 minutes. And standard deviation of a population we know is sigma. So sigma is 10 minutes. The past month, Mary has decided to try a new route, and over a period of 20 days. So 20 days tells us that's my N. Over a period of 20 days that she used the new route, the variance in terms of time has been 64 minutes. So now this is referring to sample data. And interesting, I don't know if you picked up, the word variance was used, and yet earlier on standard deviation was referred to. Now we know that there's a relationship between standard deviation and variance. Standard deviation is or variance is standard deviation squared. So the sample data is given to us as variance. So the standard deviation of that sample is actually 8 and the variance is 64. And so when we go back and we look at our population data to compare, we see that we weren't given the variance of the population data, we were given the standard deviation. However, we can very easily work out the population variance by just squaring that 10. So the population variance is 100. Now remember, the population data is the data that should be in your null hypothesis and your alternate hypothesis. So we can already state our null hypothesis and our alternate hypothesis. Although we need to establish what the question asks we should test. Is it going to be greater than, less than, or equal to? So we continue reading. At 95% confidence level, now 95% confidence level is 5% level of significance, and by implication the alpha is 0.05. At 95% confidence level, conduct a test to determine if the variance between the old route and the new route is the same, and that tells us what kind of hypothesis we're going to be using. We're going to do a two-tailed test because we want to work out if the old is the same as the new. We don't want to try and establish is the one greater than or less than the other one. We want to know, is it equal to or is it not equal to? So how will we state our null hypothesis? Our null hypothesis will have the population parameter in it. And because it is variance we are testing, this is a chi test. We need to test the variance of the old route and the new route. Using the population data, we'll say the variance is equal to 100, and therefore the alternate hypothesis will say the variance is not equal to 100. We can then work out either our test statistic or we can work out our critical values. Whichever one you do first is not as important as getting them both right. But let us do the test statistic first. So the chi-test statistic is n minus 1 times my sample variance divided by my population variance. And so that would be 19 times 64 divided by 100. And I calculated this to be 12.16. Okay. So, what we also know is because of that equal to sign in the null hypothesis and the not equal to sign in the alternate hypothesis, we need to say alpha divided by 2 because it's a two-tailed test. And we've said because variance is asked for, we need to test the variance. Chi is the test that we're going to use. And when chi is used, we know that it is a non-parametric population. What this means is that we will have two critical values, but they won't be the same. To work out those critical values, we go alpha divided by 2 is 0.025, and that would be my lower end. To work out the upper end, I would say 1 subtract 0.025, and my upper end would therefore be 0.975. To get these values, I have to read off the table, off the chi table. So, if I toggle my screen and I go to the chi table, and I've taken the liberty of highlighting the relevant row, at 19 degrees of freedom, and we got 19 degrees of freedom by saying 20 minus 1. At 19 degrees of freedom, let's start with 0.025 is 32.852. The higher end would be 0.975, and that critical value is 8.907. So I'll just repeat that. I won't repeat it. I'll just basically trace my cursor all along this line so that you can see where I obtained those values from. And then for this one, it is 8.907. Okay, so going back to the question, I'm going to change the color of my pen to indicate. Change the color of my pen to red, so that when we write these in, I'll write them in a red so that you can see the difference. I said that 0.025, the critical value on my upper end was 32.852. The critical value on my lower end was 8.907. So what I do now is I have to conclude. So I use my test stat and I see where does my test stat fit in here. My test stat seems to fit in this area, in between my two critical values. And the area in between my two critical values is known as the non-rejection area. That is the test stat, which is 12.16. On either side of my critical values would be the rejection area, but I'm not going to reject. I'm going to accept my null hypothesis. So, if I am now to conclude, I would say that at 95% confidence level, there is enough statistical evidence or significant statistical evidence to accept the null hypothesis, which states that the population variance is still 100, and I therefore reject the alternate hypothesis, which states that the population variance has changed or is not equal to 100.